Welcome to Math 106, Chapter 0.4, where we talk about how to factor and solve. So it says a zero of a function is a value, or zero of a function f of x is a value of x for which f of x or y is equal to 0. So in other words, we are finding the x-intercepts, the roots, and solutions of that particular function. So keep in mind, I'm going to say it one more time because the sentence contains a lot of value. It says a zero of the function f of x, keep in mind that is y, is a value for which the x, when you insert it in, will make y equal to 0, which is exactly what an x-intercept is. This is when x is some number and y is 0. Or f of x is equal to 0. Now, those words are interchangeable. So x-intercepts, roots, solutions, zeros, they all mean the same exact thing. So on the graph below, can you identify the solutions of this particular function? Well, your solutions, right, is where your y is equal to 0. Your x-intercepts, meaning that you have solutions for your x. This is when x is equal to -3, when x is equal to 3, and when x is equal to 7. Now, a while ago, we talked about evaluating functions. Right now, we don't have enough information to figure out what our formula is for this particular graph. We could do like a very elementary version of it, but without much context, right? This is as far as we can go, right? However, we know that if we did have a formula, if we insert a -3 into your function and evaluate, the output would become these zeros. Now, is this still a function? Well, your function was just to draw any sort of vertical line, and as long as it hits your graph once, we have a function. So this is still a function even though your y values repeat, even though you have several solutions, that's okay. It depends on the type of graph that will produce different solutions, how many solutions it does have. So let's try example 1. So solve the linear equation. So when we go to solve, we know that solve, we're looking for solution. We're really looking for your x-intercept at times. So your x-intercept, where x is some number that we don't know, but we do know that your y is equal to 0. Therefore, the y that's over here on this side, we can just set equal to 0 and then start to solve. Now go ahead and pause the video, see if you can find the solution. Find what x is. So we can add 7 to the other side. That's something that we would want to start with when solving. Definitely take care of any constant first to drag over to the other side as far as a linear approach goes. So you get 7 is equal to 1/2 x. Now, how do we get rid of this 1/2? Right? This could be rewritten if you feel more comfortable instead of a fraction. You could really just merge that right underneath, multiply the 1 to the coefficient of x, so the ghost 1 in front of the x, if you want, and then 2 multiplied to the denominator. So now that it's in this form, if you feel more comfortable, you can now see that you're going to multiply both sides by 2, or on the other side, you can just multiply by the reciprocal. And I'm going to scoot this over just a tad. Give myself just a little more room. You could, if you have a fraction, just multiply by the reciprocal. So flip it upside down. And that way it cancels, the 2 cancels with the 1 on the bottom, and the 1 is just 1, but let's say it was a different number, right? It'll cancel no matter what. And what you do to one side, you have to do to the other. Now, you don't have to keep dragging the 1 on the bottom because it is just a 1. But in either case, you're left with 14 is equal to x. So again, on the other side, those 2's will cancel, right? You're trying to do the opposite action. So 14 is equal to x. If we put it as an ordered pair, when I put a 14 in here, right, to show you, we know that x is equal to 14, to 1/2, we put in our 14 minus 7, 14 divided by 2 minus 7. So that is 7 minus 7, which is equal to 0. So we know that your y is equal to 0. So that is proof of the case. We have solved it. Now, if we wanted to quickly draw it as well, we certainly could, kind of just giving you a little bit more, right? Well, where is your x-intercept? Well, 14 being positive is somewhere over here. Let's just say this is 14, comma 0. And if we're drawing a line, right, ignore your slope. What's your y-intercept? Well, your y-intercept is -7. So that would be maybe somewhere down here. 0, -7. And we can just draw a line straight through. And that would be your line if you were asked to graph it. Not necessary. I know I didn't ask for it, but I like to kind of just see what skills we picked up from previous examples. So your y-intercept you've seen from previously, and now when you are asked to find the solution you're trying to solve, all you've done is just found your x-intercept. Now, linear equations, right, lines, how many solutions do they have? Right, well, in order to stay linear, right, it means that we only have, and as we see, this one solution, right? Lines, they are nice and straight. We cannot dip back down to try and touch your x-axis again. So we only have one solution, one x-intercept. One solution, one x-intercept. Now, if we talk about quadratics, at most, how many does a quadratic function have? A quadratic function, think about y is equal to x squared, right? Linear. We have y is equal to x as its parent function, right? So y is equal to x squared. How many at most do you have? If we were to draw a quick picture, maybe you need more of a visual. A quick picture for a quadratic. Just a parent function, y equals x squared. How? Well, actually, right now we see one solution, right? However, if I were to draw it again, let's say I draw it one more time, take it away. How many solutions would I have if I drew my parabola up here? Well, here I'd have none. Let's say I flip that one upside down and it came down here. Well, I have two solutions, right? 1, 2. So at most, right, we just saw a case where we had 1, we had none, and we have 2. So at most, we can have is 2 solutions. That kind of signifies here, and we'll talk about multiplicities and how to graph them in the future, right? But at most, for a quadratic function, we're going to have 2. And kind of it goes and follows its degree or its multiplicity, right? The degree of this x linear is 1. The degree of your quadratic is 2. And if we kept going, cubic 3. And this is at most how many they can have. All right. If we are to continue on, it says the most common and fastest way to solve a quadratic is to factor. So notice that we didn't have to factor for linear. So if it has a linear approach, if it has a degree of 1, we don't have to factor. However, if it's not a linear function, and if it's a quadratic, cubic, quartic, you name it, some sort of polynomial, most likely we're going to have to factor. Now, factoring, where we want to start, is a GCF. Now, what does GCF stand for? GCF stands for greatest common factor. And we always want to perform a GCF test before we get right into factoring. So that's why we kind of started off here first. So factor by finding a GCF, right? Greatest common factor means what do all terms have in common, right? Terms are separated by a series of addition and subtraction signs. So if we have these three terms, what can you see that they all have in common? Well, we can see that they all have an x in common, right? But how many x's, right? Well, they only have one x. Now, to break it down slowly, if you need this, what I'm going to show you highlighter method, awesome, stick with it. But my hope is that eventually you don't need this little highlighter method. Now, when we come in, this is a very elementary case, but when we take a look at these, we also want to take a look at their coefficients. Now, can you write out all of their coefficients? You'll notice that you have a 3 here. This is the coefficient of 3, or x squared coefficient is 3. Now, what's technically in front of that x to the 4? Well, that would also be a 1, and again on the x. Now, what do these coefficients have in common? Right? Well, they all have a 1 in common, so we can just kind of write out their coefficients. 1 and 3, 1 and 1 again. And what we're going to end up doing is we're just going to highlight what they have in common. They have just one of these ones in common. You can only highlight one. Yes, this one has 2 and that one has 2, but you can only highlight 1 for 1. Now let's take a look at this x to the 4. How many x's are actually in x to the 4th? Well, there's 4 of them. So let's go ahead and write out these 4. And again, write out these 2 and then the 1. Right? So we're really just writing out what or how many x's they have. And if you had more of your variables, you can keep writing them all out. Now, as far as the highlighter method goes, now highlight 1 for 1 how many x's they have in common. Well, there's only this one x here. So that means of each of the next term, we can only highlight one x. Now, the highlighter method goes just says anything that got highlighted gets to be taken out. Well, I highlighted the 1 and I highlighted the x. Just one x and the 1. Now, you don't have to show that the 1 is out in front. It's what we call the little ghost 1. It just kind of follows us. So now on the inside, the leftover bit is anything that didn't get highlighted from the term. So in this first term, what didn't get highlighted? We got a 1 and how many x's? 1, 2, 3. So you could say 1x cubed. And the sign can follow us. We didn't take out a sign. Okay. We now have our next term as a 3x. And your final term, kind of separating it as a plus sign, the final term, we took out a 1x, meaning that we left behind this 1. So your final answer should be this whole thing, where your GCF is right here. Your greatest common factor of all your terms, we took out a 1 and an x. Now let's see if you can pause the video and try that method, or if you already know it, continue on, pause the video as much as you need. All right, so here we have negative 2x squared minus 4x. I'm going to do the same highlighter method and then just kind of explain it. If you already know what the answer is, awesome. You can kind of just skip. All right, so here, 2 and 4, what do they have in common? Well, they have 2 in common. So let's write each coefficient in terms of 2. So that'd be a negative 1 times 2, a negative 2 times 2. Now we do the same thing with your x's. How many x's are in the first one? 2. And how many in the second one? Just 1. Now let's go ahead and highlight what they have in common. Well, they have a 2 in common, just one of the 2's. They also have this negative sign in common, so we're going to factor it out. And typically you factor out if your leading term is negative, we want to factor that out. Now, what else can we factor? Well, we can also factor out one of these x's. So on the outside, we took out a negative, a 2, and 1x. Now, we do have a sign change because we have now factored out a negative. So that is going to switch to a positive, and you can write that right below it if you need it. Now, left over in your first term, everything that got highlighted, we're not going to look at. It's anything that's not highlighted. So 1x plus, because the sign change, right? It was negative to start. We took it out, so it's going to undergo a sign change. And now the leftover bit is 2. Now, again, you don't have to keep writing these ghost ones. So your answer, a better answer would look like this. That one is okay, though. But again, make sure you are taking out that negative. And I'm going to just kind of show you where all of it comes from. If leading term is negative, factor it out. If both are negative, or all, I should say, factor out. Let's try it again with this one. So -3, 9, they both have a 3 in common. So let's go ahead and write them in terms of 3s. A's, how many A's we have in that first one? We have 1, 2, 3. And I'm just going to keep writing. We have 1C, 1, 2, 3, 4. Okay. So now let's go ahead and highlight. We did say if our leading term is negative. So right here, you do have that leading term, right? Your leading term typically, we haven't talked about the structure yet. Your leading term should always be the highest degree. Now, as long as this one has a high degree, let's say we have 5, 6, we have 6, 7. Actually, this one should come first. But the way it's written, again, we have it. I'm not really going to nitpick, but in its structure, because this one is out front, we'll just take it out. So let's go ahead and factor out that negative. We're going to factor out just one of your 3's, 1A, 2 B's. Don't like how I did that. 1, 2, 1, 2, and 1C. So on the outside, we should have -3A, B squared, C. Now this undergoes a sign change, and because we're factoring out the whole negative, this also now becomes a negative. This becomes a positive, the other becomes a negative. And you can always double check by factoring your GCF back in. Left over, we have a squared here. We have now -3C cubed. Again, these being your GCFs, GCF, GCF. So again, good way to check. Is to factor back in. So factoring back in, you're multiplying, okay, this whole thing into here. So you get a -3. There's 1A here and 2, meaning we get 3 A's, then B squared C, which is exactly what we had here. We're multiplying a -3 times a -3, which makes a +9. Then again, A, B squared. You got 1C and 3 C's to make 4. So that is A-okay. So now we're going to get into a little bit more factoring detail. We're going to be factoring binomials and then solving. We can solve these through other means, which I will show you, but we're going to really focus in on the factoring. So anyone see or anyone know what these first two are called, A and B? They have a special name. These are called difference of squares. Difference of squares, they're easy to spot. You only have two terms where the middle term, typically your x term, so bx here and bx here, they are missing. So it's really just the x squared term and your constant. Now, even better is that they're separated by a subtraction sign and everything in sight is a perfect square. What I mean by that, if I look at A, is that your perfect square, right? Right here, if I were to write it out, How many x's are there? Well, there's two x's, right? A perfect square is a number multiplied by itself. So x is already squared. X squared is just x times itself. 25, what number makes up 25? Well, it's 5 times itself, 5. So a perfect square. These are examples of perfect squares. What other perfect squares do we know? Right? Well, 9. 9 is 3 times 3. 1. 1 times 1. 6. 6 times 6. Right? It's a number multiplied by itself. So we're going to write out 5 as its perfect square. So here, right? And we're trying to factor. So factor to solve. Do we have any GCF to pull out? Well, unfortunately, no, there's no GCF. They have nothing in common, but we always want to check first. But what's nice about it in this form is that because everything's the same, we can write two x's and two 5s. And then all you have to do in order to get your middle term to cancel out means they have opposite signs. So make one of these positive and one of these negative. And these are all still equal to 0. Now let's put these into parentheses. If you already know how to factor these, go from this step all the way down here. And again, you could factor to check or FOIL to check. Now that we have it here, when we go to solve, just as we did with kind of your domain where we were talking about excluding values, if we know the property that a times b is equal to 0, it's either that a is equal to 0 or b is equal to 0. This in itself, this is a, this is b. They're both set equal to 0. So we get to set our factors equal to 0. So x is equal to -5, so subtract the 5 over. And x is equal to, add the 5, so x is equal to 5. So that just says if we were to put these solutions back in, I'll just check one of them. Let's say x is equal to -5. We have -5 squared minus 25 is equal to 0. -5 times itself is 25, a positive 25. Minus 25 is equal to 0. 0 equals 0. That is true. This is another great way to check your solutions. Now, this is just by solving means. We'll talk about at the very end of this video, I might go back and show you, or I'll show you now. Another way, this is by solving. No, I'll wait till the end of the video. Let's have you do it again here with B. Pause the video, see what you come up with. All right, so we do have perfect squares. So 4 is a perfect square of what number? That would be 2 squared. X is already squared, that's nice. What about 81? 81 is 9 squared. So what I get to do, and I like to do it, I like to write out my 2 2s, my 2 x's, my 2 9s, and then from here, just alternate your signs. Make one positive, make one negative. Put them into parentheses. And this is factoring by solving. Again, if you already understand it, you can jump right to here. You don't need this stuff. On a test, if I say factor by solving or solve by factoring, this is what I'm looking for. So from here, we can just go ahead and set them equal to 0. All right, from here, subtract the 9 or add the 9 on the other side. Divide by 2. X is equal to -9 over 2, and x is equal to +9 over 2. That just means if we were to plug them all the way back in, they would come out with a 0. And I'm going to highlight my final solutions. Now keep in mind quadratics, these are all quadratics. All of these are quadratics. We can have 2 solutions. We could have none, we could have 1. What's going to come up is that if you have 3 solutions, something is wrong. Now, when it comes to different variations, like C, right? C is not a perfect square setup. Instead, it does have a different approach. If you wanted You could certainly write this out as having x minus 1 and x minus 1 minus 4. FOIL, combine like terms, and then factor the traditional way. A shortcut to that, though, is that because this is all squared, what we need to do is move your constant to the other side. So step 1, if it's in this form, you want to move the constant to the other side. So we can add the 4. So we get x minus 1 squared is equal to 4. Now that it's on one side, and on the other side, you now have one term that is fully squared. Now we could take the square root of that value. Do not take the square root to begin with, because square root properties, just because that's squared, it doesn't undo it. It doesn't just go away, right? It's a full binomial now. You cannot just do this and then this as well. That doesn't work. It has to be this whole thing. So now square root all, or square root both sides. Now this is the most important step over here. So I'm going to highlight that one. All right, so we can square root everything. Now when we square root everything, we must account for a plus or minus sign. Put plus minus square root on this side. The reason for that is that if you understand the quadratic formula, right, part of it already has the plus or minus sign in it, because you're going from a function that has two solutions, right, at most two solutions, to now, and I'll redraw that to show you the actual two. You go from something that has two solutions into one that now has only one, meaning that you have lost one of your answers along the way, both a positive and a negative response. So for us, we need to account for that with the plus or minus. Now what's nice is that on one side, this directly cancels, and I'm going to put that in a different color. So it gets x minus 1 is equal to plus or minus the square root of 4. Now, what is the square root of 4? The square root of 4 is 2. So we now have plus or minus 2. And then we have two solutions to one solution. We are missing so now it can be treated as linear. X is a linear. It's just 1, or a degree of 1. So now we can go ahead and add the 1 to the other side. So is equal to 1 plus or minus 2. Now when it comes to your solutions, we can have 2. 1 plus 2 and 1 minus 2. So x is either equal to 3 or it can be equal to negative 1. And again, we can check your solutions by plugging it back into the original problem, always the original, to see are they accurate. And there you go. Let's try it again with D. See if you can pause video and try this one out. All right, so thankfully your coefficient, hold on. I totally forgot to finish out the step-by-step 3. So you squared both sides, and now you simplify. And step 4, solve for x. If x is linear, then regular solving. If x is quadratic, then factor solving. What I mean by that is if it had a degree of 2, then you would solve a traditional way. But for the most part, I think they're just going to have a degree of 1. Okay. So thankfully, 1 has already been moved over for us. So we can go ahead and square root both sides. Now, when we said we square root both sides, what do we need to account for? The plus or minus sign. So we can just do plus or minus 1. So we get 2x plus 3 is equal to the plus or minus square root of 1. Now, what is the square root of what? Well, it is a perfect square of itself, just 1. Now, if it's not a perfect square, what we can do is figure out, well, can it reduce at all? Or is it prime, meaning that it, or is it not prime, but if it can't simplify, then it can stop. And I'll talk about simplifying here in a little bit. All right, so if it's just 1, now we can go ahead and solve. It has a degree of 1, so let's solve it the traditional way. Move the 3 over first. -3 plus or minus 1. Divide everything by 2. So x is equal to -3 plus or minus 1 over 2. So we have our two solutions, -3 plus 1 over 2, and -3 minus 1 over 2. So up top, we get -2 over 2, and down below, we get -4 over 2. So your x values, your solutions, are -1, and x is equal to -2. And there you go. Now, I do want to show you one extra method, not so much factoring, and I'll just do it on this particular one, B. Let's say we didn't want to solve, but we are doing any method. Sorry, we didn't want to factor, but maybe we just wanted to solve it. So if we have 4x squared minus 81 is equal to 0. So same sort of idea as the one previous. We want to get your coefficient alone. So move your coefficient to the other side, add the 81. 4x squared is equal to 81. It's positive. Now let's go ahead and get your x squared term alone. We want to divide both sides by 4. And unfortunately, they are not divisible with one another, so they have to remain as is. So now that your one term over here is nice and squared, right? It's all squared. What we can do is go ahead and take the square root. Now you do that to both sides, but keep in mind what we need to add to your square root sign. Every time you create your own, you have to account for the plus or minus sign. Again, that comes into play with your different solutions. So we have x is equal to plus or minus the square root of 81 over 4. Now we do know what your answer is. We do know that it's -9 over 2 and +9 over 2. How does that relate to this one over here? Well, 9 is the square root, 81 is the square root, or 9 is the square, perfect square, right, for 81. And same thing with 2 and 4. So that must mean we should be able to break up these square roots, which is exactly what we want to do. The square root of 81 is 9. The square root of 4 is 2. And you have your plus or minus sign. So your answer here is just x is equal to plus or minus 9 over 2. And it's okay to leave it in this form. If you want to separate it, that's totally fine. And you can do that again in this form for 25. Drag over 25, square both sides, plus or minus 5. Now we're going to move on to factor by grouping and solving. Now, factor by grouping is nice because it's easy to spot. You always want to look for a GCF to start, as always. But with factor by grouping, if we're supposed to group, it has to be nice and even, meaning that they need 4 terms. So looking at A, we have 4 terms, 1, 2, 3, 4. So 4 terms here. Now, when we want to go ahead and look for your GCF, do these have anything in common? Unfortunately, they don't have anything in common. Yes, all 3 of these have an N, but notice that the 4th term doesn't. So we can't just pull out one N to start, because then you have a negative N, and that doesn't work. So no GCF. So instead, let's go ahead and group. So first thing we want to do is group your first terms. So step 1, group 2 and 2. All right, so now step 2, now that everything's grouped, look for a GCF of each pair. So looking at these 2 terms, what do they have in common? Well, hopefully if you need, pause, do the highlighter method, okay, if you need it. but they both have a 4 and 2 n's in common, leaving behind a 3 and an n, and we took out all of that term, right? All of that term we're left with is 1. Now, what we need to make sure is that on your next parentheses, when you go ahead and do your GCF here, we need to make sure that your parentheses are the exact same. So when you look at this one, right, what would you pull out if we already have 3n plus 1? And I'll set that to 0. What on earth can you pull out? Well, they don't have anything in common other than a what? They only have a 1 in common. And notice that because they match and they're the same, we don't want this to change, meaning that we can take out a positive 1 in order for it not to change. Try to have a sign with it, whether it's a positive or a negative sign, doesn't matter. For ours, it has to be a positive 1. Okay, if they were both negative, maybe you take out a negative 1. Okay, but you have to take something out. Now, what's nice is that once you've factored it out, your GCFs, so put GCF into parentheses. So in one parentheses, you have your GCF, and in the other, you have the same exact term. Now, the reason why this is that, well, what do 4n squared, and then this term, and then plus 1 and its multiplied term, what do they have in common? Well, if I were to highlight what they had in common, they both have a 3n plus 1. So you end up factoring it out from your term, and your leftover bits becomes your GCF. From here, we can go ahead and then start to solve. So 4n squared plus 1 is equal to 0. 3n plus 1 is equal to 0. 4n squared is equal to negative 1. We can divide by 4. That's fine. N squared is equal to negative 1 over 4. Anybody see something that's wrong? Now, underneath the square root, right, are we allowed to have a negative sign? Hopefully, previous instructor said, no, that is not allowed because it creates an imaginary solution. Because the reason for that is that, keep in mind, this is still a quadratic. Can you have negative solutions or negative values for your x counterparts? Yes, you have a negative and a positive. So negative here is okay. However, when we go and switch this into a square root function, our negative answer is okay. Or negative solutions, your x values, okay. No, there are no negatives, but there are positives, meaning that any negative solution is not okay. So we have no real solution. Although we have two imaginary solutions. The imaginary is coming from the property, and I'm going to put it over here, the property that the square root of negative 1 is equal to I. So if we can prove that there is in fact a negative 1 under here, that it is considered an I. So if we were to kind of backtrack with the negative 1 over 4 underneath the square root, we can say, okay, well, there's a negative 1, or I should say, what is making this a negative? I might even put it that way. Well, it's really a negative 1 times a 1/4, all under that plus or minus 4. So from here, right, we can separate the square root, again, all positive and negative, times the 1/4. So this fact here is now justifiable. We can see that it's here as well. So we have a plus or minus I, and then we have the square root of 1 over 4. Just like previously we said, hey, when it comes to having two values on top and on bottom, we can separate them with its own square root. We only need to account for one plus or minus sign. So we could say that this is really 1 over 4 like that. Therefore, it's 1 over 2. So all together, when we're talking about two imaginary solutions, we have plus or minus 1 over 2i. Now, not all of them go in so much depth. Your next one does have an imaginary solution. It's just not as complex. And again, let's have you start B, and then when you hit the imaginary, if you're still having trouble, um, just unpause the video. All right, so do we have a GCF? No, not all terms have an M, not all terms have a 2. So instead, we're going to go ahead and group your first two, your last two. In my first two pair, we can take out an M squared, so 2 M's, leaving behind an M minus 1. In your second group, we can take out a positive 2, right? They don't have, they're not both negative. The first one is not negative, so we don't have to take that out. So we're leaving behind an M. And because we took out the 2, we're leaving behind the 1 in its place. And again, use the highlighter method if you need. Now that we have we factored out, and notice that these two are the exact same. That's awesome. We can continue. So in our first parentheses, we can have one of these. And order doesn't matter with your parentheses, just as long as you've grouped them. So now we can go ahead and set them equal to 0. M is equal to 1. M squared is equal to negative 2. M is equal to plus or minus the square root of negative 2, which here, again, we can pull out and just say, okay, well, this is really negative 1 times 2. So plus or minus the square root of negative 1 and the square root of 2. Now, negative 1, right? What could we say that one was? Well, negative 1 is really I. So this is really plus or minus. Now, can we do anything with the square root of 2? Does that simplify? No, so that doesn't simplify any further. So I square root of 2 or plus or minus the square root of 2i. Doesn't quite matter. So we still have those solutions. And you'll notice here, I totally forgot to find my other solution. Don't be like me. 3n is equal to negative 1. I always find a way back to if I find some sort of mistake. So again, you have solutions. Now, how many solutions do we actually have? Well, we said we have 2 imaginary, so that's 2, and then we have 3. But we're not working with a quadratic. Instead, we're working with a cubic. So it's okay to have 3 here. Same thing over here. We're working with a cubic. You have 1, 2 from the plus or minus, and then the additional 1. So let's go ahead and look at example 5. I'm so sorry, because we're talking about, oh, no, that's fine. All right, so example 5, we're talking about traditional factoring. So we're going to start with the easier of the two, simple factoring. So when it comes to simple factoring, we know it's simple factoring when we have this particular form, ax squared plus bx plus c. So we have all three terms. And even better, it's when your a term is equal to a positive or a negative 1. Now, if a is negative 1, we want to factor a negative out from all terms and make them positive. That way, we're not stuck with trying to figure out what to do with the negative, and it just makes it so complicated. It's easier if you factor out the negative to start. So let's go ahead and take a look at the first one. So do we have simple factoring? Well, your leading coefficient here is that ghost 1a. Perfect. So in that case, what we get to do is we're going to look at factors of C. Look at C and find factors. Okay, so factors of 12, we have 1 and 12. What else do we have? We have 2 and 6. We have 3 and 4. And then we have to stop. So next, which factors of C can make B? And you're probably like, what's C? What's B? Keep in mind, ax squared plus bx plus c. So of these factors, what can make a 7? Well, 3 and 4 can easily make a 7. Now, ours is positive 7, meaning that how can our 3 and 4 make a positive 7? That is only if they are both being added. So we can say, okay, well, 3 plus 4 make the positive 7. That's B. And if we were to multiply those two together, they still make our positive 12. So that's good. Now, what's nice about simple factoring is that once you find your factors, you can just put them into parentheses. X plus 3, that's one of them, and x plus 4 is equal to 0. From here, we can go ahead and just solve. If you want to skip that step and just go right for -4 and x is equal to -3, that's perfectly fine. As far as work goes, for any sort of test, what I'm looking for is something like this, definitely that, and then these. So unnecessary step is maybe a little bit of this, maybe a little bit of that, or give me something to work with. All right, B. Let's see if you guys can pause the video and try it out. Oh, and I keep forgetting to finish out these thoughts. Step 3, check. And then step 4, place into parentheses. All right, let's try it again. So you have factors of 9, 1 and 9, 3 and 3. Now, of those factors, what will make a -6? So 3 and 3 can make 6, but we want a -6 to come out, meaning that ours will both be negative. Now, if you struggle with this particular point, what we can do is just give it a guess. There's only 3 or 4 different ways. You can start them off both positive. You can start them off with both negative. You can interchange them. Right? But either way, there's only 4 different ways that you can check to see, okay, which one is the correct way. So from there, you found your, you found what works. You're checking it to make sure that it still comes out to be a positive 9, which it does. And then we get to go and put them into parentheses. X minus 3 is equal to 0. So x is equal to, and you'll notice that both of these, because they are the exact same, what you could do is just say x minus 3 squared is equal to 0, right? Just like what you have up here, right? You've just kind of simplified it a little bit, or even right here, you've simplified it. There's 2 of these that you've just decided to condense. For us, there's 2 of them. We're going to condense it. Now, when you go to solve it, it's really just the inside part, or you can, if you want to, take the square root of both sides, but it's going to be 0 on this side no matter what. So it's really just going to be 3. It's going to be only one of these 3s. You do not need to repeat. Let's have you try it again with C. Now you notice that C setup is slightly different. You have one term on the other side. However, it's still a quadratic, meaning that we need the setup ax squared plus bx plus c. So that just means that we need to shift over your term. So step 1, get all terms to one side. X squared minus 13x is equal, or sorry, plus 12 is equal to 0. Now notice that I put it in its spot, right? This is bx, and I know it because it has a degree of 1. Ax squared has a degree of 2, and c is just without an x. So make sure you put it in its correct spot. So if there was an x squared over here, make sure you put it front. If it's your constant, you're putting in the back. And again, you're just going to do the same. Make sure that too, you're also checking for a GCF. There are none, unfortunately, on these counterparts, but always want to be looking for GCF. So we're looking for factors of 12. Now, which one can get us to a 13? Well, 1 and 12 can get us to 13. And we want a negative 13 to come out, meaning that both of these have to be negative. And if we were to multiply them back together, we would get a positive 12, which is exactly what we have here. So x minus 1, x minus 12 is equal to 0. Therefore, x is equal to 1, and x is equal to 12. Again, I kind of want to highlight us just kind of putting it in. There you go. So that is simple factoring. Now we're going to do one more, which is complex factoring. So complex factoring. So if simple factoring was when your leading term A was either a positive or a negative 1. The complex is the opposite of that. Notice your A value of B, C, A, B, and C. So complex is when A is not equal to positive or negative 1. And you'll see that all of your A values here are different. So in our case, we're only adding a couple extra steps. So for us, and I only teach 2 different ways of teaching complex factoring, but don't feel like you are limited. If you already know how to factor and you're good at it, great. But don't limit yourself. If you don't like the 2 that I teach, please go and explore. All right, so the first one I'm going to teach, and I like to teach it, is the AC grouping. It's pretty traditional. And then I also teach slide and divide, which I'll show you at the very end of this video. So AC grouping. Step 1, check for a GCF. Do we have a GCF? No. So step 2, multiply A times C. So A times C, and again, AX squared plus BX plus C is equal to 0. So 2 times 3, because A is equal to 2, B is equal to -5, and C is equal to 3. So we have A times C, which is equal to 6. So now we are going to find factors. Okay, factors of C. Factors of C, 1 and 6, 2 and 3. Now we're going to do exactly as we've done before. Which factors? Which factors add / subtract up to B? So B is 5. So which one can make a 5 through addition or subtraction? And again, if we're not sure, because 1 and 6 could make 5, right? 2 and 3 could also make 5. We could try them out, right? There's nothing wrong with guessing and checking. So if you did select 1 and 6, you could say, okay, well, 1 minus 6 makes a -5. That's great. But when you go to multiply them back together, that makes a -6. Meaning that ours, though, is a +6. 3 was positive, 2 was positive. So does this actually work? No. So this actually doesn't work. So you can always test out your theory, but check it. Make sure that if you have multiple ones that work, which isn't often, you definitely want to make sure to check some of your values. So now that we know that 2 and 3 are going to be our ones, how do they make the 5? Well, they both have to be subtracted in order to make 5. And with those signs, when they multiply by a negative by itself, they'll make the +6. So this one is the correct one. So step 5 is an additional step. Typically, we can stop here with simple, but complex, we have to take it a step further. We're going to replace factors or replace B with factors. Replace B with factors. So 2x squared, instead of writing B as -5, we're going to write it as -2x, because keep in mind, this is an x term, this is bx, minus 3x. Order doesn't matter. Okay, you could easily swap these two, but notice that if you were to combine them, they go back to -5. So all you have done is you are now changing the look of that middle term. So now all you have to do is factor by grouping. So pause video, see what you can come up with. How did we do? Again, factor by grouping. I have lots of videos on factor by grouping. So if you're not quite getting it, definitely go check some of those out. Keep in mind you're grouping the first two and pulling out a GCF. So make sure you look at your GCF if that's what you're struggling with. All right, let's try it again on B. So do we have a GCF? No. So we're going to multiply, and I like to write out my ABCs. I like to multiply A times C. So 5 times 3 make 15. Okay, well, what are factors of 15? Well, there's not much, but that's okay. Now we are trying to find how to get -8. So trying to get -8 with 5 and 3, we need a -5 and a -3. And if we were to multiply those signs back together, we do get a +15. So we found the correct pair. So let's go ahead and rewrite your middle term using the 3 and the 5. -3x minus 5x. And notice that order doesn't matter. You could be strategic and put the -5 first and factor it out. But let's say, because order doesn't matter, I just want to show you that it really doesn't matter. You can mix it all up. So your middle term becomes that. Now let's go ahead and factor by grouping. Right, your first group, we pull out an x. Your second group, notice how close it is. We're off by a sign. So we can factor out a -1 and switch all of your signs. And now they're the exact same. X minus 1 and 5x minus 3 is equal to 0. So x is equal to 1 and x is equal to 3/5. If you need to slow this part down, just add the 3, divide by 5. I think we're all capable at this point to jump here though, because this is a calculus class. We need to make sure that we can get to the right spot. All right, so I'm going to show you slide and divide. Now, the first two steps are still strategic in sort of like you would do this no matter what. So you'll notice that we're not in the traditional form of ax squared plus bx plus c is equal to 0. So we need it to be. So step 1, get into standard form or your general form, meaning that we need to be strategic in the way that we pull it over. So notice that we have a negative x squared. So we don't want the first term to be negative. So we want to perhaps pull all terms to the other side. That way it switches these two sides. 5x squared minus 18x minus 8 is equal to 0. So this now, right, all of your signs can switch, make it 0. And again, still try to get into that form ax squared plus bx plus c. So now look for GCF. Oh, actually, yeah, look for GCF. I'm going to label this as slide and divide. If you are a forgetful person, do not do this method. Okay, it is so not worth it if you do not, if you are very, very forgetful. So slide and divide just says, okay, step 1, check for GCF, check. Unfortunately, we do not have a GCF. So step 2, we're going to slide A to C and multiply. Sounds familiar, right? So slide A to C and multiply. X squared minus 18x minus 40 is equal to 0. So no step 3, find factors of your C. And you'll notice that when you slide, you no longer have to represent the 5. So factors of 40, 1 and 40, 2 and 20, 4 and 10, 5 and 8. So of these factors, right, listed out, which one can get us to 18? Use factors to get B. Well, that would be the 2 and the 20 to get to negative 18. So 2 and 20, and we need a negative 18, which means the bigger number gets the sign. So 20 being the bigger number, that one has to be negative and 2 has to be positive. When we multiply to check, we do get negative 40. So that is it. Now this is where the forgetfulness comes into play. So we're going to take the 2 and the 20, and we're going to divide by what we slide over. So divide by A. Our A happens to be 5. A is equal to 5. So we're going to divide by 5. So 2 divided by 5, that doesn't give us much. Negative 20 divided by 5, though, that makes negative 4. So now we get to put factors into parentheses. So we get x plus 2/5 and x minus 4 is equal to 0. Now we don't typically leave the 2/5, especially if we're just asking to factor. Instead, you bring the 5 right in front of the x. So 2x plus 5 and x minus 4 is equal to 0. Therefore, x is equal to 4 and a negative 2/5. So that is slide and divide in a nutshell. Again, I'm going to highlight the part where most students forget. I do not recommend this this method if you have an issue with forgetting. I'm going to probably just stick with the AC grouping because there's less forgetfulness in that method. All right, now before we wrap it up, we are going to talk about the points of intersection or the break-even points. So points of intersection or break-even points is the intersection of revenue and cost function. And to find where they intersect, right, notice that on this particular graph, right, locate its intersection points. Well, where they intersect, right, is where they end up meeting. Well, where do they end up meeting, right? This is where they end up being equal to one another. These are called your break-even points, right? You're not losing or you're not gaining anything. This is where you're kind of at like a stalemate almost. You're break even. So step one, you're going to set the equations equal to one another because you have two equations. One of them looks like it's linear. The other one looks like it's some sort of quadratic. Step two, bring all terms to one side and solve. The reason why we want to get things to one side is notice that in all of these, it's equal to zero, equal to zero, equal to zero. That only happens when you bring all terms to one side and there's nothing left. So find the points of intersection. Absolutely. So to find the points of intersection, right, notice that both of these start with y equals. So when both are y equals, we said bring them together, set them equal to one another. X squared plus 1 is equal to 4x. So step one, bring together. Step two, set equal to each other. Step two, bring terms to one side. Now, again, you want to be strategic. Whichever has the biggest degree, so ours being the x squared, if it's positive, those terms are going to come to it. If it's negative, we're going to bring it over. So for us, let's go ahead and bring over your 4x. So let's subtract the 4x to the other side. Now set it equal to 0. Step three, factor and solve. All right, so factor and solve. Do they have a GCF? No. Okay. Well, no GCF, that's okay. Now, factors of 1, well, that's just 1 and 1, right? That doesn't work. That can't get us to 4. So this just means that it's not factorable. So if it's not factorable, we still need to solve, right? So factorable, I'll write it over here. If not factorable, that doesn't equal it's not solvable. We just can't factor. Therefore, we need the quadratic formula. Anybody know what the quadratic formula is? The quadratic formula, maybe you've had teachers in the past have you memorize it, says x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This is not something that I will be giving you on the test. It is something that I would expect you guys to know. Now, where are these A, B, C's coming from? Well, that is just coming from the general form. You have your A's, you got your A, your B, and your C here that are going to map to the above. So for us, our ABCs, A is 1, B is -4, and C is 1. So when we say x is equal to, right, it says negative b. So negative b is 4, plus or minus the square root of b squared. Minus 4, regular 4, that's always going to be there, minus 4, times a, times c, all over 2 times a. And that's your setup. Now, all we have to do from here is to simplify. A double negative makes a positive. Square root of negative, or sorry, the x or -4 squared, that will be 16. That should always end up being positive. -4 all over 2. So -16 minus 4, that's 12. Now, no, you cannot cancel and simplify yet in this form. However, let's take a look at the square root of 12. What are some factors of 12 that we know of? Well, factors of 12 are 1 and 12, 2 and 6, 3 and 4. Now, of these factors, do we have a perfect square, a number times itself? Well, 4, right? So if we look at the square root of 4 and the square root of 3, notice that any of these factors, you can break it up in its own square root sign. But what is the square root of 4? 2. What is the square root of 3? Can't go any further, right? It just means that the square root of 12 could be broken up into 2 times the square root of 3 and still come out to be the exact same. 4 plus or minus the square, or plus or minus 2 square root 3 over 2. Now that all of your terms have a 2 in common, right? This 2, that 4, if you wanted to, you could factor out a 2 at the beginning, right? But we can reduce each by 2. And that would be our final answer. And I'll just write what I did here. Reduce all by factor 2. Now, if you struggled with simplifying a non-perfect square, I do have a video, it should be maybe on the very next one, that talks all about this, on how to do that reduction, okay? Quadratic formula, that will never change. If you do see it on the test, it will be kind of nice numbers. This is kind of plain and simple. You might see a more realistic one on a test, but keep in mind, quadratic formula is not something I'm going to easily give you on the test. So that is all about factoring. Again, there's lots of support videos after this one in case you are struggling with factor by grouping, simple, or complex factoring.